Look around you. What do you see? Perhaps you see the walls of your room, or the screen you're reading this on. Maybe you can see the sky outside your window. Everything appears smooth and unbroken. When you move your hand through the air, it glides effortlessly. There are no bumps, there are no gaps. It feels continuous, like a perfectly calm surface of a vast, endless ocean. This is our everyday experience of the world. We live in what seems to be a seamless reality, a reality where you can always imagine dividing a distance in half and then in half again, forever and ever. There seems to be no end to how small you can go. This idea of a smooth, continuous universe is deeply intuitive. It's what our senses tell us every single moment of our lives. It's the world that classical physics, the physics of Isaac Newton, described so perfectly for centuries. But what if this smoothness is just an illusion? What if, when you zoom in far, far beyond what any microscope can see, you find something completely different? What if the fabric of space itself is not a smooth sheet of silk, but something more like a finely woven tapestry made from countless individual threads? Imagine walking on a sandy beach. From a distance, the sand looks like a single uniform surface. It appears perfectly smooth, a golden carpet stretching out to meet the sea. Yet, we all know the truth. If you kneel down and look closely, you will see that the beach is made of countless tiny grains of sand. Each grain is a separate, distinct object. The smoothness was just a trick of perspective, an illusion created by the sheer number of grains and our distance from them. Could space itself be like this? This grand question, whether space is a smooth continuum or a collection of tiny pieces, is not a new one. In fact, it's a debate that has echoed through the halls of philosophy for over 2,000 years. On one side of this ancient argument were philosophers like Zeno of Elea. He proposed a series of famous paradoxes that seemed to prove that motion should be impossible if space were infinitely divisible. On the other side were philosophers like Democritus and his teacher Leucippus. They proposed that everything in the universe, including the very stuff of reality, was made of tiny, indivisible particles. They called these particles atomos, which in Greek means uncuttable. For a very long time, the idea of a continuous, smooth space won the day. It was the work of Sir Isaac Newton in the 17th century that truly cemented the continuous view of space into the foundations of science. Newton gave us a new way to see the cosmos. He described a universe that ran like a magnificent, predictable clockwork. His laws of motion and universal gravitation explained everything from a falling apple to the majestic dance of the planets. And the stage upon which all this cosmic action played out was a very specific kind of space. It was absolute, infinite, and perfectly smooth. In Newton's universe, space was like a giant, empty, three-dimensional grid. The beautiful smooth canvas of classical physics began to show its first tiny cracks at the turn of the 20th century. The trouble didn't come from studying space itself, but from studying light and heat. Physicists were trying to understand a seemingly simple problem called black-body radiation. According to the classical physics of Newton, their predictions went disastrously wrong. The solution came in the year 1900 from a German physicist named Max Planck. He suggested that energy was not continuous. He proposed that it could only be emitted or absorbed in discrete little packets or chunks. He called these packets quanta. A few years later, a young Albert Einstein took Planck's idea one step further. He used it to explain the photoelectric effect. Einstein proposed that light itself was made of these energy packets, which we now call photons. This meant that light was not just a continuous wave, as everyone had thought for a century. It was both a wave and a particle. It was grainy. It was quantized. This was the true birth of the quantum revolution. The discovery that energy comes in tiny packets, or quanta, was just the beginning. This new science was called quantum mechanics, and it was unlike anything that had come before. It described a world that was fundamentally fuzzy, probabilistic, and weird. Think about an old-fashioned light dimmer switch. You can slide it up and down, and the light changes its brightness smoothly and continuously. This is how classical physics viewed the world. Now think about a modern three-way light bulb. It has a few distinct settings: off, low, medium, and high. You can't get a brightness that is in between low and medium. This is the world of quantum mechanics. An electron orbiting an atom can only exist in specific energy levels, just like the settings on the light bulb. It cannot exist in the gaps between. It has to jump from one level to another without ever existing in the space between. If space is indeed made of tiny, indivisible units, then our universe has an ultimate resolution. We could call these units pixels of space. This smallest possible length is often called the Planck length. To put that into perspective, if you were to scale up a single atom to be the size of the entire observable universe, a Planck length would be about the height of a tree. Trying to see a pixel of space is far beyond our current technological abilities. It would require a particle accelerator the size of our entire galaxy. So how can we possibly find out if they exist? Scientists are clever. They are looking for indirect clues. They are searching for tiny imperfections in the smooth fabric of space-time that we observe. One of the most prominent attempts is a mind-bending theory called loop quantum gravity. Loop quantum gravity proposes that space is not a smooth, empty backdrop at all. Instead, it's actually a real physical thing, an active network woven from countless tiny, discrete loops. Imagine a piece of fabric like, say, a chainmail shirt. From a distance, it looks like a solid, smooth surface, but up close, you can see it is made of individual, interlocking metal rings. Loop quantum gravity says space is like this. The universe is a vast, intricate network of these fundamental loops. Each loop carries a tiny, quantized amount of area. These loops then link up to weave the three-dimensional space we experience. There is another great contender in the race to unite gravity and the quantum world. It is called string theory. Think of a guitar string. You can pluck it in different ways to produce different musical notes. They are all just different vibrations of the same single string. String theory says the universe works in a similar way. All the different particles we see are not different things. They are just different notes being played on these fundamental cosmic strings. The universe is a grand cosmic symphony, played out on these unimaginably small, one-dimensional strings. And here's the crucial part. For the mathematics of string theory to work, the universe must have more dimensions than the three of space and one of time that we know. These extra dimensions are thought to be curled up or compactified into a tiny size, far too small for us to see. So we have these brilliant competing ideas, but science is more than just beautiful ideas. To be science, an idea must be testable. And this is where we face the single greatest challenge in all of modern physics. The scale we are talking about is almost impossibly small. If we cannot build a machine big enough to see a pixel of space, perhaps we can use the universe itself as our laboratory. The cosmos is full of natural experiments that involve incredible energies and vast distances, far beyond anything we could ever replicate on Earth. One of the most promising ways to search for the graininess of space is to look at light that has traveled for billions of years from the farthest reaches of the universe. To test this, astronomers turn their most powerful telescopes towards the most violent and energetic explosions in the cosmos, gamma-ray bursts. By carefully timing the arrival of the different colors or energies of light from these distant blasts, scientists can look for the telltale delay predicted by some theories of quantum gravity. It is an experiment that uses billions of light-years of space as its apparatus. So far, the results have been tantalizing but inconclusive. This has allowed scientists to rule out some of the simpler models of quantized space, but it doesn't mean space is smooth. The search continues, with every new gamma-ray burst providing another chance to test the very fabric of reality. While astronomers look to the heavens, other scientists are looking for clues in laboratories here on Earth. One ingenious idea uses huge instruments called interferometers. These are the same kinds of machines, like the LIGO experiment, that were built to detect gravitational waves. One of the most mind-boggling ideas is that a pixelated space might not be a static grid. At the Planck scale, the very geometry of space might be constantly boiling and bubbling, a seething quantum foam of tiny, fleeting distortions. The hope is that this incredible sensitivity might be enough to detect the effects of the quantum foam. This would show up as a tiny, persistent noise in the instrument's data, a fundamental fuzziness that cannot be eliminated because it comes from the very nature of space itself. So far, no such fundamental noise has been found. The experiments have placed strict limits on how foamy spacetime can be, ruling out many theoretical models. But the quest pushes onward. Scientists are designing new experiments, pushing the limits of technology to achieve even greater precision. These experiments, both on the ground and in space, represent the frontier of our search for the ultimate nature of reality. The question we began with remains one of the most profound and unanswered puzzles in all of science. Finding out whether space is quantized is the key to unlocking the next great revolution in physics. It is the necessary step to finally uniting the world of the large with the world of the small. A final, unified theory would allow us to understand the places where our current science breaks down. We could finally describe what truly happens in the singularity of a black hole, or what occurred in the first fleeting moments of the Big Bang. This quest also pushes us as a species. The incredible experiments designed to search for the subtle clues of a quantized space are marvels of human ingenuity. This pursuit of fundamental knowledge is a testament to our innate curiosity. Think of the universe not as a painting on a smooth canvas, but as a magnificent woven tapestry. When you stand back, you see the grand picture, the swirling galaxies, the brilliant stars, the vast empty spaces. But if you were to step closer, closer than anyone has ever been, you might see that the image is made from individual threads. You would see the intricate weave, the knots, the loops. You would see how the warp and weft of these fundamental threads create the illusion of a continuous image. The colors and shapes are not painted on. They are an integral part of the fabric itself. This is perhaps the most profound shift in perspective. If space is quantized, it is not an empty stage. It is not a passive container for reality. It is reality. Space is a physical thing with a structure, a texture, and a story to tell. And so we look up at the night sky with a new sense of wonder. Is the darkness between the stars a perfect, featureless void? Or is it a fantastically complex network, a quantum foam bubbling with potential, a tapestry of unimaginable richness and detail? We don't yet know the answer, but asking the question has already transformed our view of the cosmos. It reminds us that reality is almost certainly stranger, deeper, and more beautiful than we can possibly imagine. The search for the smallest unit of space is, in the end, a search for the ultimate nature of everything, and that is a journey worth taking.